Okay. Hello, everyone. As you all know who I am, my name is Emily Rivas, for those who don't know. And I designed a custom square Helmholtz coils for the Ray experiment under the supervision of my PI, Rena Mary Young. So to reiterate, what exactly is Ray? Ray stands for Rydberg atoms at Yale, and this is an axion search experiment. And with axions, it would simultaneously solve the existence of dark matter and the strong charge parity problem. Like Alpha and Haystack, it is a haloscope experiment. And through the inverse Primakov effect, an axion is passed through a strong static magnetic field in which it can spontaneously um, become a photon with the frequency corresponding to the axion's mass. However, through haloscope experiments, when a major challenge when searching for axions at masses this high, um, it is the time that it takes requires becomes increasingly long due to the lower signal and high increased quantum noise. Ray takes a different approach by using a single photon detector, in which we use a 405 nanometer laser and a 975 nanometer laser to excite an alkali atom. In our case, we are using a potassium atom, and once excited, this atom becomes a very large high principal number, thus becoming a Rydberg atom. Once this Rydberg atom has been ionized, we use a channel electron multiplier to count its electron. And through this, we are able to use the Rydberg atoms to detect single axion microwave photons. So why Helmholtz coils? When it comes to when we first found these Rydberg atoms and we were able to detect them at the beginning of this year, we initially ran a simulation with Eleanor simulation that it was supposed to be a single Gaussian peak. However, when we did detect them, we saw two peaks as seen here. We weren't sure why it was exactly happening until Professor Charles came up with some theories. And in one of those theories was that it was a straight magnetic field. Here, the two peaks signify two substates of the Rydberg atoms. And once we figured out that the AIM gauge magnet, which is a pressure sensor that contains a magnet, was causing the straight magnetic field of around 5 Gauss, we were able to take it out because now that we are at the point of the experiment where the pressure in the system has stabilized, we no longer needed the pressure sensor. So with the prototype, we wanted to induce a magnetic field, and I created one single axis Helmholtz coils. These are the coils, the white here and the yellow, and it has the selective field ionization chamber inside, in between where the magnetic field would be most uniform. And this is exactly where the Rydberg atoms would be, where they would be excited with the two lasers. And with the prototype, we were able to distinguish that the more magnetic field that we added, the more separation of the two substates we were able to achieve. And we wanted to separate these two substates because it was when we only have one peak, the two substates are right on top of each other. But when they're right on top of each other, we don't have a good signal and a good focus of what we actually want to see. So separating these two substates further from each other would allow us to focus on just one thing at a time. So inducing a magnetic field not only allows us to induce a controlled magnetic field, but also it would allow us to cancel out the Earth's magnetic field. So canceling out any stray magnetic field in the system entirely. And we aimed for about 20 to 30 Gauss because we were already using inducing a 5 Gauss with the prototype coils. So 20 to 30 Gauss would definitely separate these two peaks, two states completely. And although we do have a supply of 20 amps, we aimed for 15 so that the coils and the wire that we were using wouldn't overheat entirely. When it comes to designing the coils, one, Ray has a very limited space, which you will see later on. So it was very particular that we made sure that we didn't take up too much space and that we didn't block any optics in the system. So the innermost coils, as you see here, were the ones hardest to design because this is where every other coil would be mounted onto. So it has to be the most stable, but it also has to be the smallest. And we used 3D printed frames because we didn't want to have any strain on the system. So already adding the weight of the coils was already enough, and machining these parts will add too much weight. Eleanor came up with the idea of adding holes on the sides for the heat dissipation of the coils in case they did overheat, but it's highly unlikely due to the fact that we are using such low amps because we tested out different coils that were made in 2021 by Yuki, in which she made anti-Helmholtz coils. And with the coils that she made, we tested out how hot it would get with 20 amps. And it was around 30 to 40 degrees Celsius. And with using 15 amps maximum, we'll be fine. And Eduardo came up with the clamp design in the middle so that the whole system would be stabilized. And then the leads for the coils, which are down here, came up with the idea from Talia once discussing with her because it didn't go through my mind at first, but thank you. And with that, I was able to look back to Yuki's coils and see how she was able to integrate leads for them. And instead of using a simple ordinary circular shape like I did with the prototype, and I went for a more rectangular design, more of a square shape, because the uniform magnetic field that I wanted to focus on was only a few millimeters at the center. So the difference between a uniform magnetic field at that small thing with a circular or a rectangular shape wouldn't really be much of a difference. And also a rectangular coil shape is much easier to mount. So here's the Ray system. This small part right here was the hardest thing that made it difficult to mount the inner coils because the coils couldn't be so thick and they couldn't be very wide either because they had to have a good enough distance to satisfy the constraints and the equation of a Helmholtz coil. However, these connectors were then easier to mount the middle coils and the outermost coils. And those are the ones that I also 3D printed, and I just used regular screws. And then I used nylon screws for the wires, in which I connected to a 10 gauge wire to connect to the power supply. I would like to thank my PI, Professor Reina Mariyama, for letting me have this opportunity and be in this lab. And thank you for Professor Charles Brown for helping me and guiding me throughout the coils as well. And also thank you very much to my mentors, Eleanor and Eduardo, for guiding me and providing me the learning experience and the information required to carry out this presentation and my time here in the lab. And of course, thank you to the Yale Summer Experience Award for allowing me to have the ability to live in New Haven. Thank you.
How did you get the foil holding system to fit so perfectly around the Ray setup?
So Eduardo was able to send me the CADing for the race system. So I was able to get all the dimensions from there. Yeah.
Why, when you 3D printed, did the filer
So for this small little thing, and also this pipe here, I wasn't able to wind the inner coils outside of the system first and then put them on. I would have to put them on and wind it on the system, which was a very big hassle, but pulled through. And with that, I would have to mount the inner coils first, wind them on the system. And it was also because it doesn't show the optics here, the optics, I would have to work around it. So hands started cramping, everything was going. But originally everything was working. And I also had to make sure that I didn't cover this optics or this one here. But yes.
What is the number of turns and length of the foil? Because my coils do much more than
Right.
the setup.
So your coils that I saw were very tiny. You used a 24 gauge?
Yeah.
Yes, a 24 gauge and were many turns. But those were also going to cryo. For me, Ray is still in its room temperature state, and we are just doing room temperature experiments. And with these coils, especially the inner coils, it'd be a hassle to wind 200 turns onto the system, right? So having a nice thick and a thick coil in which we were able to find rectangular wire that was let's say it was 0.3 inches thick and 0.02 inches thick and 0.03 inches wide, so that we were able to fully just cover one layer of coil with just one turn instead of doing multiple columns of turns.